Alrighty, howdy folks. So this is chapter 7, section 2. We're continuing with that replacement analysis. But then we are looking at what is the optimum replacement interval, right? So for instance, if you choose to replace your car, when would be a good time? That's the kind of analysis we are doing here. Okay. There are situations in which an asset needs to be replaced at certain intervals. For example, rental cars by a rental company, a simple machine like a lathe or a drill, etc. Does it make sense? Like rental car people, right? I mean, they cannot keep that car for a very long time. Pretty soon they would have to change. And that's why when you rent a car, you tend to get a pretty recent one. We won't have a whole lot of miles on it, right? Sometimes you may end up getting something that has basically barely 100 or 200 miles on it, right? Okay. Now, replacement is necessary because as equipment ages, operating and maintenance (O&M) costs tend to increase. At the same time, the cost of ownership tends to decrease with increased usage. Right? When you own an asset, um, you would have paid some money to own an asset, but then by next year you would have depreciated, so you would have lost some value. So the cost of ownership tends to decrease with increased usage. Now, this figure over here explains that concept fairly well. For example, in this graph, we have three curves. The first curve is the annual O&M cost indicated by the red line. So it's a straight line. And what this is saying is the annual operating and maintenance costs keep increasing every year. That kind of makes sense, right? If you buy a car, man, the first year you won't have a whole lot of costs. Uh, but then pretty soon you will have to do some servicing, and that adds up costs. And maybe after that you may need to replace the timing belt. All sorts of things keep happening. So the assumption here is the annual operating and maintenance costs would be increasing every year. Cool. And then um, annual cost increases. And what about capital recovery cost? This is in order to own an asset, like I was mentioning, you would have paid some money, but then you can very well sell that right away. Typically, we don't. If you buy a car, you're not going to sell it on, the moment you buy it, you're not going to sell it right away, right? You will drive it for a while. But then what you bought for, say, $10,000, by next year, you would have depreciated to, say, $9,000. And then you keep it for a year late, for another year, then it might be only worth 7,000 or stuff like that. I'm just making numbers up here. So that capital recovery cost is shown to decrease with time. If you add these two curves, right? They are both functions of t, and you can add two functions of t. How do you do that, man? Well, what what you do is, uh, let's say at t equals 0. You take what the value of the red curve is at t equals 0, which is this y value, add to it the green one's y value, which is that. So 0 plus that, that's equal to the blue. Would you agree? Right. And then if you go to t equals 1, the red one has this value and the green one has this value. You add those two, you get the blue value. So you can keep on doing it for every value of t in this case. So that's how you find the blue curve as a sum of these red and green curves, as a sum of the capital recovery cost and the annual operating and maintenance cost. Cool. And that is called equivalent uniform annual cost. The yeah, equivalent uniform annual cost. Cool. Now comes the important question. By the way, before I ask the question, let's go back and see what was this section about? It is about optimum replacement interval. When should you, when is the perfect time to replace your asset with a newer one? Right? That's our question. Now, does this discussion about this stupid curves, economic equivalent uniform annual cost is the blue curve, does any of this answer that question? Optimum replacement interval? From the curves, can you figure anything out? The answer is of course you can. What? How'd you do that, man? The equivalent uniform annual cost is sort of the total cost. Now, the blue curve is showing that initially it's the uniform, that equivalent uniform annual cost is pretty high. And then next year, the cost decreases. And the year after that, it decreases even further. And it keeps on decreasing and reaches a minimum point at some point of time, a minimum value at some point of time. Right? This is the cost. Would you be glad that the costs have been decreasing as time increases? Yeah, man, my costs are going down. Then what happens? Well, so I'm going to hang on to it a little longer. Well, unfortunately, what happens is if you hang on a little longer, then the cost starts to increase. And so you will say, uh-oh, I should have sold it when the operating costs were really small. Ah, that's the realization. So it is possible to figure out the optimum replacement interval based on this blue curve. That is, whenever the blue curve hits the minimum value, that is the time period at which you need to do the replacement. That is the perfect time to replace. Cool. I thought that's pretty interesting when you think about it. All right. And the sum of these two costs is as shown in the figure. From the figure, can you find the optimum time to replace? The answer, the life at which the EUAC, the equivalent uniform annual cost, is the lowest, because holding past that point would only increase the annual costs. Cool. All right. Next, let's yeah. I'm not quite sure. How to find capital recovery cost as a function of time? We talked about in this previous slide, oh, there is something called capital recovery cost, and there's something called annual operating and maintenance cost. And when you add them, you get this EUAC. Okay, but what in the world is that capital recovery cost, and how do you find it? And that's what we'll talk about right now. Consider an asset that you acquired by paying P at t equals 0. I hope that makes perfect sense to you. Good. Then each year, that asset depreciates in value, say by a fraction d. Meaning you bought something for $100,000 and the depreciation is 20%, meaning zero point 0.2 is d, right? Good. That is, after 1 year, the asset, if sold, will fetch you a future value f1 of p times 1 minus d. Would you agree with that? P minus PD. It was originally P, at the beginning it was P, and so it would depreciate by P times D during that year. And so you have P minus PD, or P times 1 minus D. That is, if this is the future value for which you can sell the car, if you happen to, if you sell your asset, if you happen to sell it at the end of 1 year. Cool. All right. Now, what about this diagram? This cash flow diagram explains precisely what the situation is. You have a P here and you have a future value of P times 1 minus D, right? That cash flow diagram. After 2 years, the asset, if sold, will fetch you F sub 2. What is that now? That is P times 1 minus P times the quantity 1 minus D square. That is, at the beginning of that period, it had a value of P times 1 minus D. Now, you need to multiply that by D and subtract from P times 1 minus D. We have gone through this before also. So go ahead and, if you want to look up, go ahead and look it up. But at the future value at 2 is P times 1 minus D square, right? And the cash flow diagram would look like this. You purchased at P, and now the value is P times 1 minus D square. You will get, that's a positive. Cool. All right. And so this after T years, basically you have P times 1 minus D to the D to T. And this is the cash flow diagram for it. I hope this makes perfect sense to you. Now, what in the world is the capital recovery cost as a function of time? Okay, let's go to this example. Let me give some raw numbers. P is $100,000 and 10% is the D. Depreciation is 10. So after 1 year, what is its value? 1 minus 0.1. So 0.9 of one of 100,000 is 90,000, right? What was 100,000 a year later is worth only, according to this, 90,000. Good. So, did you lose some money? Did you pay some cost as a result of owning this asset in 1 year? Yeah, uh, it was worth 100,000 and now it is worth only 90,000. So, how much did you lose? 10,000 man, 100,000 minus 90,000. Right. But the thing is, if we say that, aren't we making that cardinal sin that you're not supposed to make in this class? I mean, I won't blame you because I was kind of thinking along those lines myself. But then after thinking a little longer, dang, I forgot that. What did I forget? And what is it that you possibly forgot? The time value of money concept. What's the difference? How much did you lose? 100,000 was in the beginning of the year. Now it is 1 year later, it is 90,000. So 100,000 minus 90,000. No, you cannot do that. You need to find the, the value of that P times 1 minus D at T equals 0. So push this guy back to that thing using your time value of money, or push this P to T equals 1, at T equals 0 to T equals 1. And then you can subtract. They must both be at the same time. That's the thing. In order to add or subtract, the time value of money should be taken into account. That is, you must have both the numbers at the same point of time. Which point of time? That doesn't matter. Could be at t equals 0 or could be at t equals 1. Right? Good. As long as we keep that in mind, we are in business. Cool. Then let's look at this guy. This t equals 2. What do we do in this case? How much did you lose? Same thing. Figure out what p is 2 years later. That's a future value at t equals 2, we are saying. P times 1 plus I, the quantity square, right? That's how we find what its future value is. If I is the minimum attractive rate of return for you, P times 1 plus I square minus P times 1 minus D square, right? That difference. Then in a capital recovery cost, please pay attention, that difference that you found must be smeared over these 2 years. Cool. Um, and we know if we have a number at t equals 2, how to smear it over 2 years. Similarly, if we are talking about a scenario, a general scenario like this, we will push this p all the way to t by saying p times 1 plus I raised to t is its value at t equals t, at time equals t, and then we'll subtract this p times 1 minus d to the t from that, and then we smear it over t years. If you do that smearing thing and find a cost in that way, that is what is called a capital recovery cost. Cool. We can now find how much value the asset has lost as a function of time. Right? The asset has definitely lost uh, some value with time. By subtracting the f sub t, that is the future time, from p. However, we must be sure to use time value of money while subtracting. For instance, the net future worth of the asset at any t is the net future worth, meaning I'm planning to choose the forward thing, the final time where I want to add or subtract these things. Is p times 1 plus I to the t, right? When you project p all the way to t, would be p times 1 plus I to the t. I is, of course, the minimum attractive rate of return, minus p times 1 minus d to the t. Cool. And now you can see that I can factor out a p. So that becomes p times the quantity 1 plus I to the t minus the quantity 1 minus d to the t. And then the capital recovery cost is just the annualized value of this net future worth. So we will smear this over t years, like I said. And how do we do that? Well, the capital recovery cost CR is nothing but this guy, that money, times I over 1 plus I to the t minus 1. So when you have a future value f, the a is equal to f times I over 1 plus I to the t minus 1. So the future value here is p times 1 plus I to the d 1 minus d to the t and all that. So this is how you find the capital recovery cost. Okay, I need to brag a little here. Man, the textbook didn't have all of this written in a clear way at all. So I was kind of pretty happy. I sat down and spent a lot of time writing down, figuring out, and in making up this PowerPoint. And then, you know, having done that, then I picked up some problems and solved them. It was piece of cake. Once I understood the concept in this clear way, tackling problems became very, very simple. Cool. Enough of my bragging. You're not here to hear me brag. You are here to learn. Okie dokie, where do we go now? Okay. Well, it also makes sense that we'll try to find how to find this annual O&M, operating and maintenance cost. Typically, O&M costs are given as a starting cost at t equals 1 that increases by a percentage rate each year. This is the key. Previously, we had a P at t equals 0. But when it comes to this cost, O&M operating and maintenance costs, it is the starting cost is at t equals 1. So at t equals 0, the operating maintenance cost is considered to be 0. But only at t equals 1, you will have some. That's when you'll start to do some maintenance work. And so you will incur some costs at the end of that first year. Cool. Then that cost keeps increasing by a percentage. Let the starting maintenance cost at t equals 1 be some m, and the rate at which this cost increases be lowercase m per year. Right? Does that make sense? Think about it. T equals m, and next year it increases by m. So that means m times 1 plus m. At t equals 2, the cost would be m times 1 plus m. The cost a year after that would be m times 1 plus m square. And so you need to raise it. It's a kind of thing that we learned about. What is that thing? Uh, multiple cash flows, um, multiple cash flows, geometric series. Yeah, geometric series stuff. Okay, so that at t equals 0, maintenance cost is equal to 0. At t equals 1, maintenance cost is m. At t equals 2, the maintenance cost is m times m. Did I say that? Ay, ay, ay. Shucks. Hmm. Do my formulas reflect that? Is the question. Yeah. So G, how do we do the G thing? I mean, these formulas that I derived, they are perfect. I checked them over and over. But when it comes to my explanation here, M, maintenance cost, yes, yeah, this is definitely wrong. Amigos y amigas, lo siento. Please forgive me. I gotta fix this. So what I need to do is say that this is m times 1 plus m. Okay. Whereas the second one is, let me just make my life easy. Be m times 1 plus m square. That's the small change I need to make. Okay. Sorry, guys. This is the problem with being mere mortal. M times 1 plus m to the t minus 1. All right, that should fix it. And I don't need to worry about any changes. Good. We are in business. The maintenance cost is m times 1 plus m, and maintenance cost at t equals 3 is m times 1 plus m square, right? And so notice how it is. The exponent is 1 less than the t. So if we go with any t, m times 1 plus m, 1 less than the t itself, t minus 1. So this is the maintenance cost, right? Now, note this is nothing but a multiple cash flow geometric series. We had I and J. J was the rate at which something was increasing. G, we had a G and a G times 1 plus I, 1 plus J, and G times 1 plus J square, the quantity 1 plus J square, and so on. Same thing. Understand that the maintenance cost accumulates over each year, unlike the uh, capital recovery, which has only two values, one at t equals 0 and the other at t equals t, right? So this maintenance cost, it's gone. Like you would have expended that. So every year your cash flow diagram, the every year that you keep, your cash flow diagram will have to reflect all the cash that you spent on this O&M, operating and maintenance, every year. And so is a and what we do is, yeah, once we explain, come on, wake up. So in a cash flow diagram, if we were to show the maintenance costs for every year, we are looking at t equals some particular time t. So what was the maintenance cost at t minus 1, t minus 2, t minus 3, at t itself, all the way up to year 1? Right? We need to show that. And then what is this annual O&M cost? You take all those cash flows and find a uniform annual cost based on that. Basically, smearing all of that uh, over the t years. That is what this annual O&M cost is. Okay, is the uniformly smeared value of these costs. Right. Now, recall that the present value of such a distribution, go back to the G thing, G times 1 plus I to the n minus 1 plus j to the n over I minus j times 1 plus I to the n. So I actually went to chapter 2, section 6 or something like that and copied this one from there. Okay. Recall that the present value of such a distribution is this. Now, in our case, what do we have? We don't have a G. Instead, we have an M, right? M is playing the role of G. We don't have a lowercase j. Instead, we have a lowercase m. I is still that same minimum attractive rate of return. Cool. All right. So annual O&M cost at any t is replacing G with an M, lowercase j with a lowercase m, but then we are smearing this out over t years. This is notice that this is the present value. And because it's a present value, in order to smear it out, I need to multiply by I times 1 plus I to the t. Had this been a future value, then I wouldn't have a 1 plus I to the t on the top. That would be the difference. Why is that? Because anyway, forget about it. So now these two things, notice these two terms cancel, and so that formula reduces to something like this. So this is how you find annual O&M cost at any t. Cool. Now, what is the equivalent uniform annual cost at t? Well, you add that CR, the capital recovery cost, and this particular annual O&M cost, and that's how you find the equivalent uniform annual cost, EUAC. This is the formula. I know this formula looks intimidating, but when you think about it, each of these parts, we know where each of these parts came, we know where from, right? That's the idea. Cool. Now let's look at a couple of examples so that this concept is crystal clear. $500,000 is invested in a surface mount placement machine. Experience shows that the salvage value for the SMP machine decreases by 25% per year. Operating and maintenance costs increase at a rate of 15% per year. The O&M cost equals $125,000 the first year of use based on a minimum attractive rate of return 10%. What is the ORI, optimum replacement interval, and what is the minimum EUAC star, equivalent uniform annual cost? First cost is P, which is 500,000. First year maintenance cost, which is our uppercase M, is $125,000. Rate of increase of O&M each additional year is M equals 15%, right? O&M cost increase. So that is our lowercase m. Depreciation rate, D, is 25% or 0.25 per year. Minimum attractive rate of return, I, is 10% or zero point 0.1. Now, equivalent uniform annual cost at any T is given by this formula that we had last time in the previous slide. Now, wonder what we need to do. Do you know that very, very difficult thing called plug and chug? That's what we need to do. Plug what? Plug all these P equals this and M equals this into all of this. But then what do we plug for T? Well, the thing is, you need to figure out for different values of T. T equals 1, 2, 3, 4, 5, 6, and all of that. Right? And that is where you are better off programming this into a computer or something like that. Like write an Excel program, or if you know MATLAB, write MATLAB, or if you happen to be C, C++, whatever, write this and figure out for different values of T. Cool. Or there is another way of doing it, which is what I resorted to doing. That is, to me, this is just nothing but one function of t plus another function of t. And I just need to add them. So that's what I did. I drew the curve. This curve is the green. And this guy, operating maintenance cost guy, is increasing like that. I think in the other one it increased linearly, but it doesn't have to be. It in fact is not. And then I added both of them all graphically. And then I also asked for us to give me, hey, give me the minimum value of this function, of this blue. Softwares are pretty good at that. And so it gave me the minimum value at A, and the coordinates of that point where the minimum value occurs is the abscissa is 4.68. So I have time on this axis, and it says, hey, dude, when t equals 4.68 years, that's when you have the minimum value for this EUAC. Oh, I see. Thanks, man. And so plotting this as a graph in GeoGebra, we see that the minimum occurs at t equals 4.68 years, which is approximately 5 years. The textbook people, this is what they do. They don't do this graphical approach. Instead, they just use a Excel spreadsheet and figure out for integer number of years, 1, 2, 3, 4, 5, and so on, 5, 6, 7. And then they just compare those values, say which one of them is smallest visually. Oh, here, good. And what they get is 5 years. Because they didn't calculate for 4.68. They calculated for t equals 4 years, and they calculated for t equals 5 years, and t equals 6 years. With 4, 5, and 6, they saw that, so at 5 we have the smallest. And so they go with 5 years like that. But then I think you and I, we can do a little more, right? We can draw graphs. We're not doing it by hand anyways. So this is how we can find this, right? Maybe. Do any of you feel like a small mathematical challenge? right? What is the mathematical challenge? Uh, what we did here, didn't we just simply, all we did is simply find the minimum value of a function? Do you recall anything about how to find the minimum value of a function from calculus 1? Simple. You find the derivative of this function with respect to what? With respect to t. The derivative of this, set it equal to 0 and solve for t. And there is that t, if it has, in this case, it should give you just one value. If it does not, will it not? No, there is no way. If the costs look like this, there is only one minimum value guaranteed. Okay, because as you can see, this keeps on increasing. And so if this keeps on increasing, after this point, that keeps on increasing. And at the same time, these values are decreasing. So you are subtracting from something that is increasing a value which is getting smaller and smaller. So the difference will keep increasing. Okay, so there will be only one solution to this. So what do you need to do? You need to take the derivative of this with respect to t and set it equal to 0 and solve for t. And guess what? If you do that, you will know exactly what the value is. You don't even, I mean, you can, if you figure it out in terms of all of this, you don't even need to draw any graphs. You have what is called a closed form solution for the uh, optimal replacement interval. Um, I might sit down and do it. I just happened to finish this PowerPoint just today, and so I'm a little on the tired side, so didn't feel like working on it. But I think sometime soon I might sit down and see if that is feasible. It'll be a lot of algebra though, but would be a good challenge. The vertical axis is scaled down by a factor of, yeah, if you see the minimum value is at t equals 4.68 and the minimum cost itself is the y value, which seems to be 2.21. That doesn't make any sense, right? What? 2.21 what? The thing is, in order to draw this, what I did is I I scaled it by a factor of 125,000. Meaning P is 500,000, M is 125,000, right? But if I factor out a 125,000, then I have 125 times 4 is 500,000. So I have 4i here and 1i here. And that's what I plotted. So if you really want to know what the minimum, like they said, what is the minimum EUAC value? You take this 4.68 and multiply by 125,000. Okay. That's because of the graphing needs. That's the idea. Cool? Whatever that turns out to be. All right. You plan to purchase a car for $28,000. Its market value will decrease 20% per year. You have determined that the IRS allowed mileage reimbursement rate for business travel is about right for fuel and maintenance at $0.505, basically 50.5 cents per mile in the first year. You anticipate that it will increase at a rate of 10% each year. So maintenance costs will go up by 10% each year. With the price of oil rising, influencing gasoline, oils, greases, tires, and so on, right? You normally drive 15,000 miles per year. What is the optimum replacement interval for the car? Your minimum attractive rate of return is 9%. So here, the only small issue is they didn't give you the maintenance cost at T1. Instead, they said you drive 15,000 miles and the maintenance cost is 0.505 per mile. So what would be the cost? 15,000 times 0.505 for the first year. And after that, that same 15,000 times 0.1 will keep increasing at a rate of 10%. Cool. All right. Now we can use exactly what we did before. P happens to be 28,000. Miles driven is 15,000 miles per year. Operating and maintenance for first year is 0.505 per mile. So that implies uppercase M is that 15,000 miles times 0.505. I should have put a parenthesis around this. It almost looks like I'm multiplying $15,000. No, that is 15,000 miles. And eventually what I get is, eh, I'm a mathematician. I should be precise in how I say things. All right. Let's take a parenthesis around it. That's the smallest thing I need to fix. Good. With that, let me save this. And then, good. So that turns out to be $7,575 maintenance in the first year. And rate of increase of O&M each additional year, M is 10% because you anticipate that it is referring to the maintenance cost, will increase at the rate of 10% each year. Depreciation rate for your car is its market value will decrease 20% per year. So that's what we are saying here. And the minimum attractive rate of return is 9%. And so 0.09. And now this is the good old formula that we have. Look at how wonderful this formula is. And once again, I plotted this in GeoGebra and the blue curve as a minimum at 5.33. So when you round it, because this is 0.3, so it rounds down to 5 years. Had it been 5.5, would have made it 6 years. But since this is 5.33, we'll round it down to 5 years. Cool. And what is the optimum replacement? Again, what I have done is I made it, I scaled it by 7,575. So that means I took M to be 1 and correspondingly decreased P. So now if you really want to know what that Y value there is, what is the equivalent uniform annual cost, take this 1.95 and multiply by 7575. Cool. That's the minimum value. Whew. Amigos y amigas, adios.